Hello everyone. So I'm gonna present some work that I've done jointly with Meven, Thibaut, and Kenji for here today. And we're going to talk about the construction of what we call AdapTT, which is a type theory which exhibits functorial properties of a type formers. So this all started with the observation that typecasts are everywhere in type theory, in the sense that there are many ways in different theories to cast a term from one type to a cast of another type. There is the obvious ones with both definitional and propositional equality, where, again, if you have T, which is of type A, definitionally equal to B, then T is also of type B. Same with propositional equality. If you have two types that are equal, you can use the J eliminator to construct a term of the second type. You have more recent works with, for example, observational equality and cubical type theory, where you have a primitive notion of transport or cast, which allows you to transport between two types. And you have less symmetric notions of typecast, such as subtyping, wherein if you have a certain T of type A, which is a subtype of B, then you can either coerce the term into a term of B or simply say that T is also of type B. In short, we have typecast everywhere. But if we zoom in a tiny bit on a few different examples of some dependent theories, we can look, for example, at the gradual type theories and, for example, gradual types, in which we have some notion of cast. And if we look precisely at pi types, we can see that the cast between two pi types is going to correspond to some lambda abstraction in which we'll do one cast from A2 to A1 and then a cast back from B1 to B2. If we look again at something else like observational equality, we see a similar pattern here. We have a lambda cast from A1 to A2, some B1 to B2. Coercive subtyping, same exact thing. When my brain looked at this, the pattern recognition parts tend to tell me that they're kind of all the same thing in one way or another. Even if we look at simpler examples, like the exponential in a Cartesian cross category, it is in one way bifunctor, and we kind of see the same thing in practice, a cast that is contravariant, and then a covariant cast over the application. What this tells me is that all these theories exhibit some sort of functorial properties, in particular for pi types. And again, this functorial property appears in many forms depending on the theory. It can be in definitional equality, in subtyping, in observational equality. So our initial goal was to have some sort of framework to talk about these functorial properties over pi types first, but then there are many other kind of types. Type formers, we have sigmas, identity, W types, and even then users can define new type formers through the use of inductive types. And so we wanted to see how we could possibly exhibit the functorial properties of arbitrary inductive types. And that's what we went and looked into. To start things off, we wanted to use as a base kind of model categories and families because they're very close to the syntax. What is a category family? It's just a certain category of context in which the morphisms will be substitutions. And basically two different functors, one which maps any context to a family of types in this context. And then given a context and a type in its context, another family, another set of terms of that type. That's all very nice, but then you have to wonder how can we have any sort of notion of coercion of functoriality between between types. And the answer to that is just to add morphisms between our types, which means that now our functor type doesn't map to set, but instead to categories. Our objects are still types, but our morphisms will now represent some notion of coercion between our types. We call these adapters in reference to Connor and Frederick's work on functorial adapters that was presented here maybe 4 years ago. I think. And yes, an adapter in a certain given context is really just morphisms between two types. And then we get that we can make this adapter act over terms such that if you have a certain term of type A, you can produce a term of type B. That should ring a bell and look a bit like subtyping or typecast in general. If we want to look into the notion of typeformers, because again, we want to talk about the functoriality of typeformers, the data of typeformers can be given as one pre-sheaf over cat D, which will give us, in some sense, the input data of our typeformer, and then some natural transformation from D to type, which on the objects will give us the instantiation of the typeformer. And then on the morphism, the kind of structural coercion between two instances of a typeformer. If we look at a few examples for type, for example, for list, for example, the pre-shape is just going to map any gamma to type of gamma. And the natural transformation on objects will just map any search term of type gamma to list of A. And similarly, on morphism, it will just be the usual map on linked list that everyone knows about. And over types, the data you need to construct a pi is going to be a certain A that acts contravariantly over gamma, and then a certain B in the gamma extended by A. The typeformer is the same as usual, and then the structural coercion between two instances of pi types will be what we've seen previously. So that kind of works. That's very nice. That's very general. It's a bit too general though. Because again, we want to look deep at the syntax and possibly look deep at inductive types themselves and see how they may exhibit functorial properties. So we're going to look at things another way in order to have a more syntactic presentation of typeformers, and in particular, some presentation that will exhibit the variance of our typeformers, whether they act covariantly, contravariantly over their input. And of course, we want that framework to be powerful enough to allow us to construct all our favorite typeformers. To do that, we have a very nice theorem that at first again looks very useful for us. The Yoneda lemma gives us that type of gamma will be in bijection with the natural transformation from sub gamma, from Yoneda of gamma to the object of a given type. Which means that in particular, sub Yoneda of gamma is a pre-sheaf, the kind of pre-sheaf that we want, and it gives rise to a natural transformation. That means that any F gives rise to a typeformer. That's awesome. Except it doesn't allow us to do anything with that. You can't really construct pi or sigma or anything interesting. And it's also just a bijection. It doesn't tell us anything about how this connects to our adapters. It doesn't tell us how it acts on one cells. To find a solution to that, we want to extend the notion of context and context extensions such that we may capture more data in those. So for example, for pi, we would want to have some kind of context gamma, which tells us that we have a certain x that will act contravariantly, and then a certain y that will depend on x and act covariantly. So these are new kinds of variables that we call type variables. And what a type variable is really just a given telescope, a telescope of variables in gamma and a certain direction to know whether the type variable is going to act covariantly or contravariantly. This works great for pi, but also for everything else, basically. It works for the identity type. This is just the parameters of the identity type. And also for sigma, we just have to say that they both act covariantly. What this gives us is that whenever we have two substitutions, sigma and theta and tau, these may map some type variables from delta in some types of gamma. We may be able to collect this information, how these type variables are being mapped between these two substitutions into new morphisms. So two morphisms between our substitutions. What we call transformation here will be the data of potential adapters between two instantiations of type variables living in delta. What this means is that our context now form a two category instead of a simple category. Now, if we look back at Yoneda, we can instead have an instance of two Yoneda, which gives us instead that type gamma is isomorphic to these natural transformations, which again means that any F in type gamma gives rise to a typeformer, but this typeformer will behave correctly with regards to our adapters. And also with our type variables, we may be able to express more complex and useful typeformers from this theorem. For example, if we look back at, just to give an example of what transformations really are, if we look back at pi types, we said that they act contravariantly over X and covariantly over Y. Two substitutions over that context are going to map X to two different types and Y to two different B's over a context extended by a certain X or over a certain A1 or A2, depending on which one you're working from. And as such, a transformation will be a bundle of data about these adapters. So we're going to have a transformation between sigma and tau will be the data of an adapter between A2 to A1, A2 to A1 and not the other way around because we're contravariant. And then another adapter between B1 and B2 in which we'll have to do a small substitution on B2 in order for this to be type correct. If we look back and have a quick summary over what we just said, we started with a category of context and a functor which mapped context to sets and context and ties to another sets. And we've enriched this notion of categories with families to have a two category of context. This is a typo, in which the one cells will be the usual substitutions, and we have a new notion of two cells that are transformations. We have now a two functor which will map context to categories, and again our terms are just usual sets. And we have a new way to extend our context with not just term variables but also type variables, which gives us all this richness that we're looking for. Now that we have all this, we wanted to be able to talk about and construct nice inductive types. Our initial objective was just to do nothing very interesting. We're not doing quotient inductive types. We're just doing parameterized, indexed, non-mutual, non-nested inductive types, the simplest thing possible. And to do that, we have now three tools at our disposal: our usual context, our new type variables, and this notion of telescopes, which allows us to talk about dependencies. How much time do I have? Yeah, that's all right. So the signature of a simple inductive type is just going to be a list of constructors, and a constructor will have different fields which are either non-recursive or recursive. So we're going to have one telescope of non-recursive arguments, and then a list of recursive arguments. And a recursive argument can be a large recursive occurrence in the sense that it may be embedded deep into a ball. So we're going to have a telescope of values over which we may do recursion. If we want to extend this to parameters, it's not that hard. We now have a new context gamma of parameters, and our telescope of non-recursive occurrences now is a telescope over gamma and not over an empty telescope. And for the same thing for our recursive telescopes, our arities now live in gamma extended by the non-recursive telescope. To add indices, again, it's not very hard. We add a telescope of indices. We now have to instantiate the indices of our structure, and we also want to instantiate any indices of our recursive occurrences with potentially values that were added in the arity of the recursive occurrence. It's just a lot of data in practice, but it allows us to make complex enough inductive types. For example, here, it's just an example of bounded W types. So it's just going to be the usual W types that will have a bounded depth, which is this natural number here. The added bound is just here to show that we can do indices, but it's not that useful in practice. We're going to have, as such, a certain context of parameters with an A that acts covariantly and a B that will depend on a certain value A and act contravariantly. We're going to have some indices, and then our only constructor sub is going to have two non-recursive fields, a natural number and a certain A of type A. We have one recursive field here in which we have a certain telescope of arity B of A, and then the instantiation for N. And then the final index instantiation for our constructor, which will give us N+1. This is just to show that this theory of signature works. What we have so far with regards to the theory of signatures is that we have typeformers, we have constructors for inductive types. We have proved and constructed the action of substitution and our new transformations over these inductive types, which means that we have exhibited the functorial properties of these inductive types. but we have yet to construct the algebra and the discrete algebra. So the constructors and the recursor and the iota reduction rules for the constructors. And we'd also like to look into potential interactions between subtyping and recursors, what we call fusion laws. To conclude, the main takeaway from all this is that functoriality of typeformers structures typecast in any dependent activity. Not just for subtyping, but all of this applies as well for observational equality, for example. So what we have so far is a nice type theory that exhibits functorial properties for pretty complex typeformers. All of this has been formalized in Agda to ensure that I wasn't saying random things that don't make sense. What we're still working on is the theory of signatures, the theory of signature with subtyping. Again, we still need to work on the recursors. And we also want to have more potential models of our new 2CWS than just our new AdapTT, which is really just the initial model of all this. And as future work, we've only talked about covariance and contravariance, but we may want to also talk about invariance and equivariance. And it would be also interesting to look into potential links between our work and some other things made. For example, the non-split, non-full comprehension categories that were presented earlier by Niyusha. And that's it.